Hello, Physics 20s. I want to take this video to highlight the principles of mechanical energy and also the work energy theorem. And all I want you to see is we are not learning new formulas per se. We're actually expanding on our understanding of work and the three types of energy that we've been mastering prior to this, right? So gravitational potential energy, elastic potential energy, and then kinetic energy. So um, energy is quite fascinating, and actually I want to just show you this animation before I show you or review the notes. So this is called the skateboard park, and you'll notice that I can measure the kinetic, the potential. I can even measure thermal due to friction, and the total energy of this skateboard guy. So I'm going to actually, it could be a girl or boy. I can't tell. I think it's a girl. Anyway, so you can see I can grab this skateboarder and place her at any position I want. So if I put her right there, she's at the very bottom, so nothing's really happening, although actually there's no friction in this analogy. So I'll get to friction in a minute. So what really it means here is if I do work on here, if I raise her up this way, and by the way, if I give her a shove like this and then let go of her, I'm actually causing a change in both her potential energy and her kinetic energy. Now, the animation doesn't show the kinetic, but if you can imagine that, it's possible to exert a force on an object. And when you do, you could change both kinds of energy. You could give the person gravitational potential energy, and you could also give them kinetic energy. So if I mean, again, I'll just get her up here and then let go of her, okay? And what you can see is the total energy, the sum of her potential and kinetic energy is what's in gold there. And then her kinetic and her potential energy keep trading places. And we can even slow this down. You can see she starts with potential energy, and then that converts into kinetic energy. And this is a really common pattern, especially when we start looking at pendulums, for example, where if there's no friction, then you have kinetic energy being converted into potential energy being converted into kinetic. But the total, like the sum total, like if I pause this at any point, right, you can look over here. If you took the green and the blue bar and you added those two together, what would you get? Well, you'd get the total. You'd get the total energy of the system. And energy is always conserved. And so we're going to hang on that really heavily for all of our scenarios here, because the total amount of energy in what we call an isolated system, and I'll define that a bit more later, but an isolated system is a system where there's no external forces acting on it. So essentially there's no friction is the big one, okay? But yeah, I mean, like I can run this animation, see right at the top, all of her energy is potential and she doesn't have any kinetic. Then on the way down, they start trading places. But look, I could pause it at any point here and we could add the kinetic and the potential, and it would add up to the total. Okay. Now let's throw in, actually, let's just throw in a different scenario where we can add friction. Okay. Now we'll just put friction at normal, and let's clear this. So again, if we start the same thing and now let her go, because there's some friction, you can see that she goes back and forth more like you would expect if you actually were in like a half pipe, on a skateboard. And what you can probably tell from this too is that, I'll do it again. If you watch, let's go in slow motion too. If you watch at any point in her movement, okay, obviously some of the energy is getting converted into heat and friction. But again, if I pause it right here, if you added up the red, the green, and the blue, guess what it would add up to? It would add up to the total. So the total amount stays the same, okay? The total amount of energy in a system stays the same if it's an isolated system. And I realize, I know I said friction was one of those external forces, but if you can actually account for friction, because you really are releasing heat to the surroundings, you can get the totals will equal that. So I kind of want you to have that in your mind as we start looking at these notes that I gave you, and I will refer to that example. So let's look at mechanical energy to begin with. Mechanical energy is EM, and you'll see that in the notes. Okay. Energy mechanical, and it's the sum of the potential and kinetic energies of a system. I think in your notes I wrote it this way. Yes, it's linear, so it doesn't matter which one you add, but I think I wrote it as EK plus EP. Okay, so mechanical energy is just the sum of those two. So the rest of this here is just trying to get you to consider what happens if you do exert a force on an object. Anytime the force is not zero, okay, then it's always going to result in a change in the kinetic energy, because if you exert a force on something, it's going to start moving. And as we said, you know, if you have a net force, means that, or it doesn't equal that, but it means that there's going to be a change in your velocity for sure. Okay, if you exert a force on something, okay, so you're going to accelerate. But you can actually, but you can, like we talked about earlier, you can cause a change in both the potential and the kinetic energies. Okay, this one says like a jet. So if you have a jet thrusting forward, you could increase in altitude and in speed, and so you'd be increasing both. Okay, so there's a couple of different scenarios we might look at here. We could do, that's what this one shows right here. It just says, like, if you could drag this mass uphill at a constant speed, see, like if the speed was constant right there, then the force up would have to equal the force down. They kind of show those little hash marks. But the so there wouldn't be a change in the kinetic energy, because it was going, you know, it's going 1 meter per second down here, and it's still going 1 meter per second up here. So there's no change in the kinetic energy, but there would be a change in the gravitational potential energy, because you got a change in height. Okay, so that's kind of this is one possible scenario, is where you move it at a constant speed. Okay, where the velocity stays constant. Now, if it's not a net force of zero, so now you got just a really big force that's just pulling it up the hill, now you definitely are going to have a change in your kinetic energy, because you're accelerating. So, you know, whatever your velocity was down here, you're going to have a different velocity when you get to the top. Like, you'd be going faster at the top. And so but the amount of work done will equal the change that you brought about in your kinetic energy plus the change that you brought about in your potential energy, because you changed two types of energies now, not just one. So to capture that, we call that the work energy theorem. It can be a little bit abstract sometimes, but and here it is right here. So the idea is that the work energy theorem, work is equal to, like, the big picture is, sure, work is equal to the change in energy. Like, that was our second definition when we studied it earlier this week. But now we're just going to define it a bit better, because it really is the change in each one of these combined, okay, because you have a change in both. So this formula is on your formula sheet. And as we tackle these, I want you to see that they expand. And so it can get a little tedious here, but I'm confident you can follow it. Okay, so yeah, here's the definition as it says there. Work energy theorem states the work done on a system is equal to the sum of the changes in. Okay, that's where that delta kicks in, that Greek letter delta. Don't gloss over that. That means often you have to expand it and define it. But so yeah, the work energy theorem states that it's the work done on a system is equal to the changes in the potential and the kinetic energies of the system. So don't worry about that concept check here. I actually started defining this first example, which I want to walk through with you here. Okay, so maybe I'll just kind of get it right up there. Perfect. So a block is moved up a frictionless plane by a force parallel to the plane, and at the foot of the incline, the block is moving 1 meter per second. Okay, so that would be V1. Oh, it already shows it. It's right there, V1. Okay. Here, actually, let's get rid of that. And then at the top, it's going 4 meters per second at the top. And at that position, it's at a height of 0.850 meters. So all that information then says what's the work done on the block as it moves up the incline. Well, I sped this up a little bit and I already wrote this. The work will equal the change in both the kinetic and the potential energies. Now, this is the part I need you to slow down a bit on, because if you say that, it means that the change in kinetic energy, you have to expand that. That's really the final kinetic energy right there, EK final, minus EK initial. That captures the delta EK. Now you got to capture the delta EP, and it's very similar. It's the final potential energy minus the initial potential energy. Okay, this is what I mean by it. So it might be a little tedious because now you have 4 things you have to account for. Okay, it went from 2 to 4 because you have a beginning and an end. So just as you read these questions, kind of follow the story in your mind, draw the pictures, do what you need to do to capture them, because ultimately this is what it looks like. We have to find the kinetic energy of the mass final, so at the top of the ramp here, and then you subtract from that the kinetic energy at the bottom, at the first part, at least according to this story, right? And MGH2 is the gravitational potential energy at the top of the ramp, and MGH1 is the gravitational potential energy at the bottom. Now, be prepared for this because it'll happen. Sometimes either the final or the initial is 0, because, like, look at this one right here, for example, the potential energy at the beginning of the ramp, because the height here would equal 0 because you're on the floor, basically. That means that MGH1 is nothing. Oh, so it's gone. Okay, so be prepared for that, because sometimes you're like, oh my goodness, I got to do 4 calculations here. Well, sometimes they are equal 0. So now I'm not going to punch in all my substitution here because I'm a little cramped for space, but I will say that if you calculate 1/2 times the mass, which is 1.2 kilograms, times the second velocity squared, okay? So that's the 4 meter per second will go right there, and the 1 meter per second will go right there, if you can follow that, okay? The mass is the same in both, but don't cancel anything because you can't. That difference there, just for the EK value, should be 9 joules. Okay, that's the change in the kinetic energy from the final minus the initial. Now the change in potential energy, well, it went from 0 to the gravitational potential energy at a height of 0.850. So we take the mass, 1.2, times it by 9.81 meters per second squared, times that by 0.85. And let me make some space here. That should give us a value of 10 point, basically it's 0.0062 joules. Okay, so sorry, I'm not subtracting, I'm adding. Sorry, I'm adding the changes in their energies. Okay, so they both have a positive change, if you will, because they have more energy in the second position than they did in the first, with both kinetic and potential, if you can follow that. Okay, so yeah, the simple answer here, I guess I should stay in black, but whatever, it's 19 to 3 digits. We'll just say it's 19 joules. Okay, so the work done would be 19. Okay, so you'll see more of these, but with work, you do have to slow down because you got all these deltas to deal with. Mechanical energy, though, is a little more clean because there's no deltas. Mechanical energy is just the sum of the energy at a position. Okay, so let's look at a quick example of that. So we've got a cannonball fired from the Earth, and at the peak of its trajectory, it's got a horizontal speed of 160 meters per second. Okay, and it is 1.2 times 10 to the third meters above the ground. Okay, so there's my H. I guess you could say it's H2 if you want. Well, it's an H. And there's my velocity. Now it says, with reference to the ground, what is the mechanical energy? There it is. So it's asking for the mechanical energy of the ball at the highest point on its trajectory, okay? The mechanical energy, would be the same in every position if it's an isolated system. Okay, so but because it's just giving you information about just this point right there, okay, then all you do is look at that point and say, okay, I want the mechanical energy at that position. So that's going to be the kinetic energy at that position plus the potential energy at that position. Okay, because it's going to have both, right? At that point, it's got a height above the ground and it's moving. Now, again, don't worry about the angle or the direction of the velocity directly, because it's energy is not a vector. That's what's super slick about energy. Okay, so yes, it would mean we'd have to go 1/2 mv squared plus mgh, and substituting in all those numbers. I think I did get, actually I did it all at once here. 1/2 times the mass, 5.2 kilograms, times 160 squared. Okay, don't forget to square that, remember. And 5.2 would be this times 9.81 times the height, which is, it's a big number, 1.2 times 10 to the third meters, no big deal. And when I get done, I get a big number. Okay, and like you saw before, I've been doing some of these practice questions. It's not uncommon to get a really big number when you're dealing with energy, because large masses that are moving or have a gravitational potential energy, they're going to have a lot of joules of energy. Okay, so yes, I do need to answer this using scientific notation. There appears to be 3 significant digits, so I'm going to round this to 1.28 times 10 to the 5th joules. That would be the mechanical energy, or the sum of both the kinetic and the potential at that position. Okay, so what I've done here is, for the rest of this assignment, I don't want you to do all the questions. I'm going to give you some more practice questions. This is just to kind of get your feet wet in applying mechanical energy and the work energy theorem. So read the questions slowly. If you can tell it says mechanical energy, there's no deltas. You don't have to blow things up. But if it is work, you got to slow down. Haha. Yeah, sorry, you have to do work to calculate work. So, and here we go. So I'll just highlight this one for you just to get you started. This mountain climber, he rappels down the face of a cliff. So it's 25 meters high. He's a 72 kilogram mass, but when he reaches the bottom of the cliff, he has a speed of 5 meters per second. What is the work done on the climber by the rope? Now, that's kind of a weird way to ask it. Okay. So, if you just simplify it and you say, okay, wait, I'm supposed to calculate work. Yes, this climber is going to experience a change in kinetic energy. What you need to kind of track in your mind is, if he starts rappelling, what would his speed have been at the top? If it doesn't say anything, we have to assume his speed is 0. Okay, he starts from rest and then he starts rappelling. Okay. And yes, the movement could be really complicated, so we're just going to go with the beginning and end here. Now, obviously at the top, he would have had gravitational potential energy, but then if he rappels down the cliff, then when he gets to the bottom of the cliff, the bottom of the 25 meters, we're assuming that we'll say he's on the ground. Okay, so his final height would be 0. So what I've done here, just to pencil it in to start you, yes, it's a delta EK plus delta EP, but the final kinetic energy, you will calculate that using the 5 meters per second. That's going to go right there. But his initial kinetic energy would be 0, because we don't have any information indicating he had a speed at the start. Okay. Now, the same thing, you have to kind of think the same way when you get to the potential energy. His final potential energy should be nothing. He's reached the ground. So you have a 0 in the MGH2 there, and it's not going to add, it's not going to multiply into anything. But then you have MGH1. So really, we have to calculate 1/2 mv squared and MGH1, and then add those two together. Okay, and that would be that would equal the amount of work done by the rope. Okay. Now, interestingly enough, you should get a negative energy here. And if you get a negative energy, the implication is that energy was lost. okay? So the amount of energy that the mountain climber had at the top, he would have lost most of that energy. Like by the time he gets to the bottom, he has some kinetic energy, so it doesn't come back to zero, but he definitely has lost energy. Okay, so don't worry about number 2. I'd like you to try number 4 and 5. And I need to mention that in the notes, but I'll post the key to this a little bit later. So when I was showing you the animation of the skateboard girl, I was mentioning something called an isolated system. What you need to know in terms of vocabulary is there are 3 kinds of systems. Now, a system is just like a set of interconnected parts, including the environment around those parts. There's lots of ways you could define it. If you study not fluid dynamics, but just thermodynamics, you address these issues as well, because there's basically these 3 right here. And this is maybe not the first time you've seen these in terms of understanding systems. There's open and closed and isolated, okay? And you can see the definitions there. Really what I want you to separate, though, are the open and closed systems, okay? Let's just maybe clear that off. The open and closed systems, okay, those are considered to be non-isolated. And in some of the literature, you'll see that because all we care about is it isolated or not? An isolated system doesn't exchange matter or energy, but really I like to add, it means there's no external forces acting on the system. I know when I was defining it before, I was mentioning friction. Typically, an isolated system has no friction, like it'll say frictionless, or the air resistance is negligible. Okay, that fun term you can say 10 times, negligible. That means it's isolated. Okay. Non-isolated systems, it will be obvious that there's been a change in the total amount of energy, and I'll show you that here in just a second. Okay, but what it means is this is the formula that defines an isolated system, because what it means is, and this is what's really powerful in terms of doing math, is you can calculate the mechanical energy of an object at one position, and then you can compare that to the mechanical energy at another position. And if it's an isolated system, like the skateboarder in the park, then it doesn't matter which 2 points you compare, but the total mechanical energy will be the same in both points. I wrote this on your formula sheet just off to the left. Instead of saying EMI equals EMF, I said EM1 is equal to EM2. Okay, and that is for isolated systems. Okay, as soon as you know you're dealing with a non-isolated system, then that doesn't hold anymore, and you would basically just say, you would just say that EM1 does not equal EM2, and that would be for non-isolated systems. Sorry, I'm just jamming that all in here, but so then the power comes, and you'll see that in a lot of these applications. You then take, so if actually I kind of wrote all over that, sorry. It just means that you could take the original expression and then blow it up. Because remember, the mechanical energy, so you would say the kinetic energy plus the potential energy in the first position. Okay, so EK1 plus EP1, then that would equal EK2 plus EP2. Okay? And lo and behold, you would get a graph that looks something like this. Okay? So this mirrors what we just saw with the skateboarder. Okay? At any position, this is showing the kinetic energy at this position plus the potential energy at the second position. Those two added together give you the mechanical energy, the total energy, which in this case, I don't know if you can really sell, it's like the dark blue or dark purple. I'm not sure what your screen is pointing out there, that top bar, the horizontal bar there, that's the mechanical energy. And you'll see, this mechanical energy, it stays the same, doesn't matter where you are, left or right. Okay, I'll get rid of that. But but in an isolated system, the mechanical energy stays the same. And so this expression holds right here, and all the other expressions that we just defined hold, okay? But you can see that, at any given position, you start here at the beginning, you have an EP maximum. You have the maximum potential energy that you can get at all in the whole system, and your EK is at 0, okay? But then they trade places as you go to the right. So as you come down the hill, your potential energy could decrease, okay? Because this is a graph of a block sliding down an inclined plane. So, or this is kind of like a cub car. So you start the cub car at the top of the ramp and then let it go. Well, all of the potential energy at the top, it becomes kinetic energy at the bottom, okay? A pretty straightforward conversion. So unfortunately, that was going to be one of the labs we were going to do in class, but you can't do it because you're not at class. So that's too bad. Now, here's the non-isolated system. I just stuck this in here so that you could see it in the notes. I know it's kind of associated with a question here that I don't want you to worry about, but this graph is really good too. This one shows a non-isolated system. And you can probably tell, or you should be able to tell from this, that it's non-isolated, because look what's happening to the mechanical energy. The mechanical energy starts right here, but then as you go down the ramp, okay, this is like a similar to what we saw before. If you just let the object slide down a ramp, some of the energy is being lost as friction. And so in this case, EM1 does not equal EM2. Okay, they don't equal each other. And yes, if you can catch that, if we were to draw a horizontal line, from right there over like this, or something like that, sorry, I just bumped it, then the amount of energy lost to friction would be that little amount right there, okay? But in this case, it's just helping you see that in a non-isolated system, EM1 does not equal EM2. Okay, and so if you needed to calculate how much energy was lost as friction, well, you would literally calculate EM1 and calculate EM2. EM1 would be right there, EM2 would be right there, and then you would get the difference between those, because that difference would be this little amount right here that I indicated before, and bang, you would have the amount of energy lost. Okay, so this conservation of mechanical energy enables you to analyze a system and determine all kinds of things. So on this one, I will post the answers to these, but I do want you to work through 1, 2, and 3 here. Okay, and maybe I will give you a hint on 3A just for starters. Okay, so we're shooting a human cannonball in the circus. So we shoot it out at a speed of 21 meters per second at an angle of 20 degrees above the horizontal. Okay, so we're going to have to analyze that probably. We're 15 meters above the ground. That's great. It does give us the mass of the acrobat, 56. So it says, what is his gravitational potential energy relative to the ground when he is at the highest point in his flight? Woo. Now it says, ignore the effects of air resistance. There's your clue to tell you that it is an isolated system. Okay, it's not a non-isolated system. We're going to treat this as an isolated system. So what it really means, and sometimes I'll do this, and I'll erase this after because there's a lot of stuff we got to do here. What it means is that EM1 at that position here is going to equal EM2 at that position there. And classically, you'll know you're dealing with a mechanical energy question if you have information to define two positions that an object is at as it goes through some kind of a movement or something. Okay, that's your clue. You're like, oh, I have the definition for 2 points. So what we would start with here, let me just switch this. where you would say that EM1 is equal to EM2. That would be our starting point. And then what we have to do is say, well, at the beginning, I'm expanding this. I'm skipping a step. You'd say that EK, here, let's do that. EK plus EP at the first one is going to equal EK plus EP in the second position. So that means that 1/2 mv squared here plus mgh1 has to equal 1/2 mv, I guess you could say 2 squared, this would be 1, mv2 squared plus mgh2. Okay, so the angle, the angle of this, the trajectory for this human cannonball, that angle is important, but not for the initial velocity. See, the initial velocity is 21 meters per second, so that's fine. Remember that energy is not a vector. However, when you get to the top of your flight, your velocity is now horizontal. Well, I was going to say you have a horizontal component the whole time, right? If you remember that. But at the top, you don't have any vertical component at all. So this is just a tip here. To get to answer this, you're going to have to go back to what you remember about kinematics, and that is if your velocity here was, sorry, what was it? 21 meters per second, then that means your hypotenuse here is 21, and the angle is 20 degrees. So what you need to find is Vx. Okay, Vy is there, but we don't need it because at the top, all you have is Vx at the top of the trajectory, if you remember. For that split second, you only have a horizontal velocity. So the second velocity, that's what I'm trying to help you see here. This second velocity is going to be Vx. Okay, so you would have to find that Vx from right here and then put it up there, and then so that would help you solve for EM2. Now, wait, I'm jumping the gun here. What am I trying to find? It says I'm trying to find the gravitational potential energy relative to the ground when he's at his highest point. Okay, so guess what? I can determine all of this, and I can determine all of this. I have everything I need to calculate those. We're doing a little bit of work here that we were discussing. I can calculate all of this. Okay, but the question is asking you to find all of that, all of it. So you're not trying to solve for the height or anything like that. I just want to know what the gravitational potential energy will be. Okay, so effectively what you need to do is calculate the first three that I've circled there, and then you would subtract that 1/2 mv2 squared. Subtract that from the right hand side, subtract all of that from the left, and then you're left with mgh2. Okay, as an entire entity, and that's your answer. Okay, so again, you can check the key for that as you work through it. Now, very last one. Oh, pendulums. Pendulums are so awesome. We are going to break them down in the next chapter. But one of the best examples of an isolated system is a pendulum. And as soon as scientists understood the mechanics of a pendulum, it should make sense to you. But the very next invention that followed the pendulum was the pendulum clock. Okay, pendulums are insanely reliable as a timing device. They do slow down a little bit due to friction, but there's ways you can add springs to keep them swinging. And if any of you have an old grandfather clock, sometimes they call them that, or maybe your grandparents actually have one, or you might be lucky and have one in your house. They're just not super common anymore. Everybody keeps track of time on their phones, and so no one really uses them anymore. But for hundreds of years, they were the most reliable timing device because of this conservation of energy principle. So if you can imagine a pendulum here, the pendulum, as you swing it up, when you get to this point, this would be your maximum potential energy, EP maximum. Okay, and you can calculate that by mgh. Now, you have to be careful with pendulums, obviously, because normally we count this line as the reference height, and so a pendulum would have no potential energy when it got back here, okay? When it swings back down, when it comes down to that point, it wouldn't have any potential energy, okay? But in a question, sometimes we define the pendulum with reference to the floor, and now it does have potential energy here. It's just that it has more when it's swung out, okay? But as you can imagine, for a pendulum, if you raise it up to this height and then let go of it, it just swings back and forth, okay? And I may post a video of Walter Lewin doing some awesome stuff with a pendulum, because basically, if the pendulum is raised to this height here and then you let it go, it will swing all the way over here, but in this place, it will not go higher than it was over here because of the conservation of mechanical energy. You could never get the pendulum to go higher than that all on its own, because it would mean that you would have to input some energy somewhere. And if you only input energy to start with, then you can't get any more total energy than that. And we'll see quickly here how basically what we would say is that the potential energy at the top of the swing would equal the kinetic energy at the bottom. And I'm really getting that because I'm saying EM1 is equal to EM2. Sorry, just EM2, not EM. Yeah. Okay, so the total energy at position 1 would have to equal the total energy at the bottom. Okay, sorry, that's just kind of ugly all around. But so what it means then is you could actually do these questions as well. So I'm going to post these shortly, because these are good questions as well, to help you understand the conservation of energy for a pendulum. So I'm going to post those answers fairly quickly here. Hopefully they make sense. And then I'll also get some other stuff up, so you guys have some things you can keep chewing on as we practice and master both mechanical energy and the work energy theorem. Okay, so keep it up, you guys.